Today we're going to talk about eigenvalues and eigenvectors. And we're going to do that by doing an example. So we're going to find the eigenvalues of this matrix here, 0, 1, -2, -3. And for each eigenvalue that we find, we'll give one eigenvector. So the steps to do this are listed here. So first, we compute this quantity, the determinant of A minus lambda times the identity. Then we'll solve this equation, so determinant of A minus lambda equals 0. So whatever we get from step 1, we'll set that equal to 0 and solve for lambda. So these two steps give us our eigenvalues. To find the eigenvectors, we plug in each lambda to this equation, A minus lambda I times the vector V equals 0, and we'll solve for V, and V will be our eigenvector. So let's go ahead and get started. So starting with our first step, I'm going to figure out what the determinant of A minus lambda I looks like. So this is the determinant of our matrix A, 0, 1, -2, -3, minus lambda times the identity matrix. In this case, it's a 2 by 2 identity matrix. So whatever size your matrix A is, that's the size of the identity matrix you'll use. Okay. Now, if we do this scalar multiplication here, because remember lambda is just a number, we'll get the determinant of 0, 1, -2, -3, minus, and now I'm just going to multiply lambda into each of these elements here. So that'll give me a lambda here, a 0, 0, and a lambda here. Okay, so now I'm going to just subtract these matrices. So I want to find the determinant of, so if I subtract 0 minus lambda, that'll give me a negative lambda here. So we're just doing element by element. 1 minus 0 gives me a 1 here. -2 minus 0 gives me a -2. And then -3 minus lambda gives me a -3 minus lambda here. This is the matrix that I want the determinant of. Move that over a little. Okay, this is a 2 by 2 matrix. So to find the determinant, we multiply A times D. So A times D, and we subtract B times C. So minus 1 times -2. And if we distribute this multiplication here and combine like terms, we'll get lambda squared plus 3 lambda plus 2. I just want to highlight this really quickly. This is the characteristic polynomial of the matrix A. So that's just something, a vocabulary word we want to just keep an eye on. All right, so we've done step 1 here. I'm going to go ahead and put a little check mark there. Now we're going to move on to step 2. We're going to set this characteristic polynomial equal to 0 and solve for lambda. So lambda squared plus 3 lambda plus 2 equals 0. I'm going to go ahead and factor that, so that's going to give me lambda plus 2 times lambda plus 1 equals 0. And the values of lambda that make this true are lambda equals -2 and lambda equals -1. So I'm going to go ahead and highlight this really quickly. These are our eigenvalues. Okay, so we just did step 2. All right, we found our eigenvalues. Now we want to find our eigenvectors. So I'm going to go ahead and go to the next page here. I've copied our steps up here just so we can remind ourselves what we're doing. We just did steps 1 and 2. And by doing steps 1 and 2, we found that our eigenvalues were -2 and -1. So let's move on to step 3. Now, steps 3 and 4, we're going to repeat for each eigenvalue. So we're going to do step 3 for one of the eigenvalues and then step 4. And then we go back and do steps 3 and 4 again for the next eigenvalue. So let's go ahead and start with lambda equals -2. That's our first eigenvalue here. So for this case, we want to plug this into this equation. A minus lambda I times V equals 0. And right now lambda is -2, so this is going to be A minus -2 times I times the vector V equals the 0 vector. And what we're trying to find here is V. So A is the matrix that we have, so that's something we know. Lambda is this -2 here, so we know that. I is the identity matrix. So the only thing we don't know here is v. That's what we're trying to solve for. All right, so let's go ahead and plug in all of our values. A is the matrix 0, 1, -2, -3. Minus -2 times the identity, that gives me a -2 here, a 0, and a -2. Okay, I'm multiplying that by a vector v, setting it equal to 0. Okay. So this is actually a system of linear equations, and if I combine these two matrices here, I'm going to get 2, 1, -2, -1. The vector v has two components. I'll call them v1 and v2. And the 0 vector is just the 2 by 1 vector that holds zeros. So this is a system of linear equations that we're trying to solve. Let me just highlight what each of these pieces is so that we remind ourselves what we're looking at. This is a minus lambda I. In this case, lambda is -2. This is the vector v, and this is the 0 vector. All right, so it's a system of linear equations. We just need to write down our augmented matrix. Augmented matrix. This looks like 2, 1, 0, -2, -1, 0. All right, now we're going to do our reduced echelon form. So I'm going to do 1/2 times row 1 and put that in row 1. That gives me a 1 up here. That's why I'm doing that. So 1/2, 0, -2, 1, 0. And then I'm going to do 2 times row 1 plus row 2 and put that in row 2 because I'm trying to get rid of this here. I want that to be a 0. So that's going to give me all zeros in the last row. All right, so this is reduced echelon form, and we can now read off the answers. So here, remember, let me move my controls out of the way here. Remember, V1 has the coefficients in this column. V2 is here, and this is our right-hand side. So this first row is telling us that V1 plus 1/2 V2 equals 0. In other words, V1 equals minus 1/2 V2. And the second row says that V2 is free because there's no leading 1 in this column. So that tells us that V2 is free. So if we write V, the vector, in its vector component form, the first element, V1, is minus 1/2 V2. And the second component is V2. We just leave that as is because that's our free variable there. Now we want to factor out the free variable just so we kind of have a sense of this underlying vector of coefficients here. So we've got V2, and I've got negative 1/2 here and 1 here. All right. So it turns out that any scalar multiple of this vector, or any non-zero scalar multiple, sorry, of this vector is an eigenvector. So this V1 here is kind of telling us that we can choose whatever we want as long as we don't pick a 0. So any non-zero scalar multiple of this vector is an eigenvector. All right, so we've answered part of our question here. We can say that the eigenvalue lambda equals -2 has an eigenvector of, and then we can just pick any scalar multiple. So you could just pick this vector, negative 1/2, 1. I'm going to go ahead and multiply this by 2 just so I get rid of the fraction. No other reason, really. So this will be negative 1, 2. So any scalar multiple is fine to put as your answer here. So this is part of our answer. Great. And we actually did, I didn't label it, but here when we made our augmented matrix, this was step 4. This is where we were solving for V. So we've done steps 3 and 4 for lambda equals -2. Let's go ahead and do them again for lambda equals 1. So back to step 3, lambda equals -1. We're plugging this into A minus lambda I times V equals the 0 vector. I'm going to skip a little bit of the algebra, so go ahead and make sure when you're doing this on your own you understand the steps here. But this matrix A minus lambda I here is going to simplify to 1, 1, negative 2, negative 2 times v equals 0. So for our step 4 here, we are going to write down our augmented matrix. Augmented matrix. That's this matrix here. So 1, 1, 0, negative 2, negative 2, 0. And then we'll do our reduced echelon form. So we'll do row reduction and we'll get 1, 1, 0, 0, 0, 0. That's our reduced matrix. This matrix is telling us in the first row that v1 equals negative v2 and v2 is free again. Okay. So in this case, we've got v equals, I'm going to put v1, so v1 in this first spot is equal to negative v2, so that's what I'll put here. And then v2 is our free variable, so I'll just leave it alone there. And we factor out the free variable, we've got negative 1, 1 there. Again, any scalar multiple of this vector is an eigenvector. So I'll just pick that one. Negative 1, 1 seems nice enough. So the eigenvalue, lambda equals negative 1, has an eigenvector of v equals negative 1, 1, or any scalar multiple of that. And that is our answer. So we found both eigenvalues, negative 2 and negative 1. For each of those eigenvalues, we found an eigenvector corresponding to it. Now in this last couple minutes here, I just want to talk a little bit about the geometric meaning of what we just did. So I'm going to label the lambdas, I'm going to give them subscripts just so we can kind of differentiate them. So I'm just going to say lambda 1 is negative 2. That's the first one that we looked at. Doesn't really matter which one you call lambda 1 or lambda 2. But you want to make sure that the corresponding eigenvector, you also give it a little 1 here, because that's the one that goes with negative 2. So this vector was negative 1, 2. And lambda 2 is negative 1. And the vector that goes with that one, v2, is 1, negative 1, or any scalar multiple of that. Okay. So what does it mean to be an eigenvalue and an eigenvector? Well, if I multiply a times my first eigenvector here, this v1 here, so this is a times v1, this is going to be equal to negative 2 times v1. Okay, so this is lambda 1 v1. Okay, that's the definition of an eigenvalue and an eigenvector. So when I distribute this negative 2, I get 2, negative 4. Sorry, move this over. All right. I can do the same thing for the other eigenvalue-eigenvector pair. So a times v2 here, 1, negative 1. So this is a times v2. That's going to be equal to negative 1 times 1, negative 1, or lambda 2 times v2. So when I distribute that, I just get negative 1, 1 here. And I want to kind of draw what's going on here. So let's draw what's going on with v1 first. So v1 is the vector negative 1, 2. So I'm going to go ahead and draw that here. I'm going to go over left by 1 and up by 2. So let me get this tool here. I've got this vector, so that's v1. Now a times v1 is the same as lambda 1 times v1. So that's going to give me the vector 2, negative 4. I'm going to go ahead and draw that as well. So I go over 2 and down 4. That's going to put me right about there. This is, maybe I'll move this over a little. This is a times v1, which is the same as lambda 1 times v1. Now, you're kind of seeing this here, that any scalar multiple of the vector v1, when you multiply it by a, you're always going to stay along this line. You're either going to stretch or shrink this vector. Sorry, this should be a straight line, but it's a little hard for me to draw a straight line. So any vector that's a scalar multiple of v will lie on this line, and that's what makes an eigenvector so special, is that all you're doing by multiplying by the matrix A is stretching or shrinking it. You're not twisting it or rotating it or anything. You're just stretching or shrinking. We can see the same idea for the vector v2. So v2 is 1, -1. So I'm going to go over 1 and down 1. That's going to put me 1, -1 is going to put me here. Okay. And so this is, let me label this v2. And when I multiply v2 by a, it ends up being the same as multiplying it by -1. So I end up at the vector -1, 1. So -1, 1 puts me there, roughly. This is a times v2, which is the same as lambda 2. Oh, running out of room here a little bit. A times v2 is the same as lambda 2 times v2. And in this case, we will always remain along this line. Any scalar multiple of v2 will lie on that line. It will either be stretched or shrunken depending on the scalar multiple, but it will always lie on that line. So that's kind of a geometric picture of eigenvalues and eigenvectors. So I hope you found this video helpful. Let me know if you have any questions.